Let us further our discussion on Dirac delta function. We will mention some more properties and solve some more problems on Dirac delta function. First, let us begin with the definition of Dirac delta function. Delta x minus a, which is equal to 0 for x different from a, and infinity if x happens to be equal to a, in such a way that the area under the Dirac delta, that is integration minus infinity to plus infinity, gives unity. And this means that Dirac delta x minus a is not equal to 0 only at the point x equal to a, and it is 0 elsewhere. Also, we showed in a previous video the following relation. This a in delta goes over to become an argument of g. With this background, let us turn to the questions now. We wish to evaluate number 1. This is number 2. This is number 3. And this is the 4th one. Note that the integrand in all the relations given contain first derivative, second derivative, nth derivative of Dirac delta function. In fact, we should not be taken aback as we did this type of integration. Let us check if we had done it. Let us quote the result. Now this Dirac delta of x minus a can be considered as the 0th derivative and can be written as and this f of a can similarly be considered as the 0th derivative of f of x evaluated at x equal to a. So let us rewrite this relation in a new garb or pattern or form as we now move over to the sums that we have decided to do. Let us consider the relation given in 1. Now delta prime x minus a is actually ddx of Dirac delta of x minus a. So the integration is and fx is considered to be the first function, while ddx of Dirac delta x minus a is taken to be the second function. We now partially integrate the above integral to get first function f of x is unchanged, and we have to integrate over the second function, and the limits are minus infinity to plus infinity. So this is the first term, and the second term is integration minus infinity to plus infinity. The first derivative of the first function f of x multiplied by integration over the second function. So this is the second term. Now integration over the second function gives Dirac delta of x minus a, because integration and differentiation are inverse of each other. So ddx goes away. The same happens in the second term also. Now we consider the first term that involves Dirac delta x minus a, which is 0 at x equal to plus infinity, 0 at x equal to minus infinity. We know that it is non-zero only at x equal to a. So the first term is 0. And we are left with the second term only. Let us apply the formula or the property of Dirac delta function, which is g of x is actually ddx of f of x? So the answer will be ddx of f of x evaluated at x equal to a. So it obviously is minus f dashed x at x equal to a, that is minus f dashed a. So let us write the result clearly. Let us be reminded of the fact that delta prime x minus a is actually the first derivative. So it is ddx of delta x minus a, and f dash a is also the first derivative of f of x evaluated at x equal to a. The superscript 1 within first bracket indicates first derivative. So let us rewrite the same relation. Using this notation that involves a superscript 1 within bracket indicating first derivative. So this is what we get. This is answer to the first question 1. If a is 0, then we can rewrite the relation as so 0 is shifted as shown. So this is in fact the second relation that we were asked to evaluate. Let us now consider the third relation. We consider the integration as given, and it involves second derivative of Dirac delta function. Let us write it or show it explicitly. So delta double prime is d2 dx square. So this is the integration. We will handle now f of x is the first function and d2 dx square of Dirac delta x minus a represents the second function. We now partially integrate to get so f of x is the first function. It stays unchanged, and now we have to integrate over the second function. And then put the limits minus infinity to plus infinity. So this is the first term, and now into the second term, integration minus infinity to plus infinity, first derivative of the first function, And then again, integration over the second function. So we get the second term. Integration over the second function gives us ddx of Dirac delta x minus a, because integration destroys one derivative ddx and we are left with a single derivative ddx. And this happens in the second term also. Now the first term involves first derivative of Dirac delta x minus a, and we can use the relation minus delta of x minus a by x minus a for delta prime x minus a. So the first term is actually this is the first term, and the limits are minus infinity to plus infinity, and we note that delta of x minus a is 0 at both the limits. It is non-zero only at x equal to a. So the first term is thus 0. We get rid of the first term and the second term survives only. And it involves now first derivative of Dirac delta x minus a, which means we have to once again partially integrate it. Let us consider ddx of f of x to be the first function and ddx of Dirac delta x minus a to be the second function. And we now partially integrate. And what we get is thus. Let us write the first function unchanged and integration has to be performed over the second function, and the limits are minus infinity to plus infinity. So this gives the first term, and we are now into the second term. Integration limits are minus infinity to plus infinity. Then we have first derivative of df dx multiplied by integration over the second function. Integration over the second function gives Dirac delta x minus a, because integration destroys the first derivative and this will happen in the second term also. Let us consider the first term, which involves Dirac delta x minus a, which is 0 at x equal to infinity, one limit, and also 0 at x equal to minus infinity, which is another limit, implying that first term is 0. So we have the second term to be present only. So we have two minus signs, which can be written as minus raised to the power 2, which is actually plus. And let us make use of the relation here. Obviously g of x is d2 dx square of f of x, and therefore the result will involve the value of d2 dx square f of x at x equal to a, that is f double dashed x at x equal to a, which is f double dashed a. Let us rewrite the result. Let us be reminded that delta double dashed is in fact double derivative, and so is f double dashed. So this is what we were asked to show in question 3, and let us rewrite this relation using the notation that 2 in the first bracket written as a superscript means second derivative. Let us now extend the result we have got. That is, write it in a general way. We had a relation with zero derivative, and this is it. We had a relation with first derivative, and this is that relation. We also got a relation involving second derivative, which is as follows. And therefore, why not have one with nth derivative? So with n, that is nth derivative, extending the previous relations, we have this one to hold also. And this is the fourth relation of the question.